So after we learn about dual theorem, let's revisit the topic of shadow prices. So let us recall the definition of shadow price. The shadow price of the ith constraint is the amount by which the optimal z value is improved if we increase bi by 1, from bi to bi plus 1. But then there's a small sign here, and then let's see what it says. It is important. It says that this assumes that after the right-hand side of the constraint I has been changed, the current basis remains optimal. So the shadow price of a constraint only applies if after the change, the current basis remains optimal. If after the change the current basis is not optimal anymore, it means that you have to recompute and obtain the optimal solution, and then using that optimal solution, interpret the shadow price. Okay? So previously we have computed the shadow price of a constraint by changing the right-hand side from bi to bi plus delta, then compute the effect on x and z. This is the third change, I believe, in the sensitivity analysis that we discussed earlier. So this is the third change, which means we're changing the right-hand side. We may still use this approach, but now in this video, we are going to use the dual theorem and see how it may help us to perform the same thing, which is obtaining the shadow price of a constraint. So let's apply the dual theorem to obtain the shadow price for Dakota example. Suppose we would like to know what is the shadow price of the finishing constraint. Now we are going to use the dual solution to obtain the shadow price. So this is the optimal solution for the primal problem. And then this is dual theorem, which says that the optimal solution for the dual is CBVB inverse. Okay, so this is CBVB inverse from the primal. We know that this is 0, 10, 10 is the CBVB inverse. And then because we have three constraints in the primal, lumber, finishing, carpentry, it means we have three variables in the dual, and then the optimal value for the second dual variable is 10. Okay. Why we're looking at the second dual variable? Because finishing is the second constraint in the primal. Okay, so up to this point, you know that the optimal value for y2 equals 10. Now, what is the relationship between the optimal dual variable and the shadow price? Here it is. The shadow price of the ith constraint of a max primal equals the optimal value of the ith dual variable. So we have obtained the optimal dual variable for y2 equals 10. It means that the shadow price of the second constraint is in the primal problem is also 10. In other words, the shadow price of the finishing constraint equals 10. So now here's the explanation of why the shadow price of the ith constraint in a max primal equals the optimal value of the ith dual variable. So here's the dual LP of the Dakota problem. And then remember that shadow price is the increase in the z value in the case of maximization problem, the increase in the z value when we change the right-hand side. So the z value before we do anything, before we increase the finishing constraint, equals this. Why we may use the dual objective function? Remember, because when we have an optimal solution, the z value equals the w value. So we may say that the optimal z value equals the w value, which is 48y1 plus 20y2 plus 8y3. If we increase the finishing constraint, the right-hand side from 20 to 21. Here in the dual problem, the objective function value will also change from 20 to becomes 21. In other words, now the z value after we increase the finishing by 1 unit becomes 48y1 plus 21y2 plus 8y3. It means that after we increase the finishing constraint by 1 unit, the z value changes by 1 times y2. And then we know in the optimal solution the value of y2 is 10. So we can say that the shadow price of the finishing constraint equals 10. Because when we increase the finishing hour by 1 unit, the change in z equals y2, and that y2 equals 10. So the shadow price of the finishing constraint equals 10. Now for a minimization problem, the shadow price of the ith constraint of a minimization primal equals minus of the optimal value of the ith dual variable. So be careful that for the minimization problem, the shadow price of the ith constraint equals minus the optimal value of the ith dual variable. So let me summarize the relation between optimal table and shadow price. If we are given the optimal table, then from the result of the dual theorem, we may read the optimal table to obtain the dual solution. Okay, so depends on whether your primal problem is max or min. You just find the correct summary, right? So if your problem is a max, find the one that says if the primal is a max problem. If your primal problem is a minimization problem, then read the one that says if your primal is a min problem, like this one. Anyway, after you read this, you obtain the dual solution. And then from here, you may say that dual solution is related to shadow price. Depends on whether is it a maximization problem or is it a minimization problem. Okay. But on the other hand, if you are given the optimal basis of the primal LP and you are also given the parameters in the original LP problem, you may directly compute the CBVB inverse to obtain the dual solution. What I'd like to say here is that if you don't have the optimal solution, but if you have this two information here, you may still obtain the optimal dual solution such that you may still obtain the shadow price. Just remember that if the primal is a minimization problem, then from dual solution to shadow price, you need to multiply the dual solution with the negative sign to obtain the shadow price. The second summary, what I'd like to say here is that once we have obtained the shadow prices, whether it is for maximization or minimization case, we may obtain the new optimal z value using this formula. Basically, if maximization, the sign here is plus the change and the shadow price. For minimization problem, the sign is minus the change times the shadow price. Okay, the reason is because for maximization, the improvement is that you're going to increase your z value. For minimization problem, the improvement is you're going to decrease your z value. So that's how we are going to use the dual theorem, which says that CBVB inverse is the dual optimal solution. And then from that dual solution, we obtain the shadow prices. And then from the shadow prices, this slide here shows how we may compute the new optimal z value. Remember that we need to make sure that the current basis remains optimal after the change. So that's the end of this video. In the next one, we are going to look at some examples in which we are going to apply the dual theorem to find the dual solution and then obtain the shadow prices. So see you on the next one. Thank you.